Let's first take a deep breath. Imagine yourself floating lightly above the starry sky. Now we turn our gaze to the blue planet beneath our feet, to its unfathomable layers of rock memory. Geologists' hammers have cracked open time's seal. At the cliff face in Gubbio, Italy, a thin band of clay lies quietly there. It marks the boundary between the Cretaceous and Paleogene periods, and seals the instant the dinosaur dynasty ended. Scientists detected an anomaly in this clay layer, with iridium levels 30 times higher than normal background values. This metal is extremely rare on Earth's surface, yet abundant in asteroids. This discovery seemed to perfectly explain the dinosaurs' extinction, a distant asteroid impact event. But the story doesn't end there. As global investigations unfolded, scientists discovered identical iridium peaks in identical rock layers worldwide, like a synchronized global fingerprint, corroborating that planetary catastrophe. Yet closer analysis revealed new puzzles. Within this iridium-rich clay, scientists used high-powered electron microscopes to uncover countless microscopic metallic spheres. These spheres were composed of rare metals like osmium and iridium. They exhibited perfect spherical shapes, with surfaces smooth beyond belief, and distributed globally in specific patterns. The discovery of these microspheres struck scientists as oddly familiar, because their appearance and distribution patterns mirrored nearly exactly findings around modern nuclear test sites. During atmospheric nuclear tests, massive energy instantly vaporizes everything, including the metallic components of the nuclear devices. These metallic vapors condense at extreme temperatures, forming minute spherical particles, which then disperse with the wind, settling globally in specific patterns. This is the unique signature left by human technological civilization, a distinct imprint of the nuclear age. Yet questions arise. Why do the spheres buried in rock layers from 60 million years ago exhibit precisely the same characteristics? In an era when mammals were only just emerging, what force generated such extreme heat? What process refined these rare metals? And what event scattered them across the globe? They lie quietly embedded in rock layers, as if silently narrating an improbable tale. The very existence of these spheres presents a geological paradox. They point to a powerful energy release, a highly refined industrial process, and a global-scale event. All these characteristics point to a conclusion we are reluctant to face. Perhaps long before human civilization, Earth had already witnessed the blossoming of another technology, and the destruction that followed. This idea is unsettling, yet impossible to dismiss lightly. Now, relax your thoughts once more. Set aside this astonishing notion for a moment. Let us carry this question as we delve deeper into the next geological stratum, to uncover more secrets buried by time. Faced with this anomalous evidence across global rock strata, the scientific community requires a theoretical framework for interpretation. The Silurian hypothesis emerged precisely in this context. Its name draws inspiration from an ancient alien race in the British sci-fi series. They once ruled Earth in prehistoric times, yet left scarcely a trace. The naming itself metaphorically encapsulates the hypothesis's core idea, that an advanced prehistoric civilization may have existed on Earth, its traces erased by the vastness of geological time. The Silurian hypothesis is fundamentally a thought experiment. It challenges the basic assumption of humanity's uniqueness in civilization, and seriously questions whether we can truly be certain that humanity is the first species on Earth to develop industrial technology. The hypothesis does not assert that such civilizations necessarily existed, but aims to construct a scientifically testable paradigm. guiding where we should search and what evidence to seek. The hypothesis posits that if an industrial civilization existed millions of years ago, its most enduring legacy would not be cities or machines, but the global chemical alterations it imposed on the Earth system. These alterations constitute what is termed a technological signature or industrial fingerprint. They are permanently recorded within the planet's geological archives. The scale of geological time is crucial to understanding this hypothesis. Earth's history spans 4.5 billion years. Human industrial civilization, from its origins to the present, has lasted merely 300 years. This represents a mere 1/10,000,000th of the planet's entire history. If Earth's history were compressed into a single day of 24 hours, the existence of the human industrial age would last less than 1/10 of a second. Against such a vast temporal backdrop, all direct material evidence of any civilization proves profoundly fragile. The skyscrapers we build will erode into dust. The steel structures we construct will oxidize and rust away. Every record we write will vanish into nothingness. Even the most durable alloys and polymers will be decomposed, recycled, or transformed into new minerals through tens of millions of years of geological activity. Yet civilization's indirect signatures may endure. These signatures manifest primarily in three critical domains: anomalous shifts in atmospheric chemistry, such as unnatural fluctuations in greenhouse gases, isotopic anomalies in marine sediments, such as unique isotope ratios produced by nuclear activity, and synthetic materials appearing in rock strata, such as polymer particles impossible to form naturally. These chemical fingerprints resist the erosion of time, sealed within stable sedimentary layers or polar ice cores, becoming messengers conveying information across deep time. The Silurian hypothesis prompts us to re-examine the geological record. It places anomalous events once deemed purely natural within a broader framework of possibilities for examination. For instance, the massive coal formation period of the Carboniferous might stem from some form of global-scale industrial activity, or the precise selectivity of certain mass extinction events could hint at non-natural intervention mechanisms. This hypothesis also sparks philosophical reflections on civilizational cycles. If technological civilizations can emerge naturally and rise cyclically, is their demise an inevitable fate of technological advancement, or a potential outcome that could be averted through wisdom? Is humanity's current trajectory of rapid development progressing along a predictable cyclical pattern? The carbon dioxide and radionuclides we emit into the atmosphere, the globally distributed plastic microbads we produce, the Earth's albedo and nitrogen cycle we alter, all these actions are creating a new geological stratum. Future researchers may readily identify the Anthropocene. Yet, if humanity's industrial civilization collapses tomorrow, archaeologists 10,000 years hence will scarcely find our cities. 100,000 years later, evidence of our existence will grow exceedingly scarce. And 10 million years from now, save for that thin layer of chemical anomaly, all traces of human civilization will vanish from the Earth's surface. This profound revelation, unveiled by the Silurian hypothesis, it compels us to examine our place in deep time with humility and recognize that the essence of seeking evidence of past civilizations is to search within planetary-scale chemical archives for fleeting, intense, anomalous signals, much like hunting for a single page torn from a library's 4 million volumes and reduced to dust. The concept of the Anthropocene is reshaping our view of the planet. Yet this concept rests upon a critical assumption: that humans are the first species to exert global geological influence. The Silurian hypothesis directly challenges this fundamental premise. compels us to rethink humanity's place within Earth's history. The geological record reveals multiple periods of cataclysmic upheaval on our planet. Some of these events bear striking similarities to the impacts of human activity. This raises profound questions about their origins. To regard humans as the sole technological species is statistically and temporally unsound. Earth has existed for 4.5 billion years, with complex life spanning over 500 million years. Throughout this vast timeline, other intelligent forms could well have existed. Human industrial civilization's 3-century history is insignificant on the geological timescale. We are repeating processes that may have already occurred. Burning fossil fuels to alter atmospheric composition, mass extraction and use of metallic materials, manufacturing synthetic substances unnatural to the environment, and even conducting nuclear reactions that release immense energy. These activities all leave distinctive marks in the geological record. If humans can create enduring geological signals in an instant, other intelligent life may have done so in the distant past. A research framework for identifying pre-civilization technological signatures is thus established. This framework encompasses 3 key dimensions: analysis of atmospheric chemical signatures. Industrial civilization inevitably consumes energy and alters the atmosphere. We search for anomalous fluctuations in ice cores and sediments, such as rapid greenhouse gas concentration shifts, or synthetic gas molecules not naturally occurring. Isotopic anomaly tracking. Nuclear activities and industrial processes generate unique isotopic ratios. These ratios are extremely rare in nature, yet can persist in geological strata for hundreds of millions of years, as demonstrated by the discovery of the Oklo natural nuclear reactor, proving that nuclear signatures endure over vast time scales. Synthetic substances and materials science signatures. Materials like plastics and alloys possess clear industrial origins. Their presence in sedimentary layers constitutes irrefutable evidence of technological activity. Even if pre-civilizations employed distinct technological pathways, the materials they produced would inevitably bear unnatural characteristics. This research framework compels us to re-examine known events. For instance, the dramatic carbon isotope fluctuations at the Permian-Triassic boundary are traditionally attributed to volcanic activity or methane release. Yet, from the perspective of the Silurian hypothesis, we must consider the possibility of large-scale fossil fuel combustion. The rapid warming pattern of the Paleocene-Eocene thermal maximum. Its speed and magnitude resemble modern industrial processes. Could this reflect the rise and fall of a technological civilization? Even the iridium anomaly at the Cretaceous-Paleogene boundary. Beyond asteroid impact, are alternative explanations possible? This framework also directs attention to specific geological carriers. Deep-sea sediment sequences are invaluable due to their continuous deposition. Polar ice cores preserve direct samples of ancient atmospheres. Clay and shale layers within stable strata offer ideal locations for seeking microscopic technological signatures. Paleosol layers may record surface industrial activity. River delta sediments may contain engineered particles. Implementing this research framework presents methodological challenges. Distinguishing genuine technological signatures from rare natural phenomena requires establishing more refined criteria. For instance, plastic particles can be identified by molecular structure. Nuclear signatures must satisfy specific isotopic composition patterns. Atmospheric anomalies should exhibit corresponding spatial distribution patterns. Temporal resolution presents another major challenge. The time compression effect in geological records may condense millennia of civilizational history into single stratigraphic layers. This demands the development of higher precision dating techniques and more sensitive microanalytical methods. The Silurian hypothesis does not seek to negate existing geological science, but rather offers new research perspectives and exploration directions. It urges us to examine Earth's history with greater openness, acknowledging that humanity may not be the universe's sole performer, but rather a note in a vast symphony of wisdom. This paradigm shift holds profound scientific significance, expanding our approach to seeking life across the cosmos. If technological signatures can persist in geological records for millions of years, then atmospheric spectral anomalies on exoplanets may point not only to life but potentially to civilization. Simultaneously, this research carries urgent practical relevance. By studying potential cycles of prehistoric civilizations, we can better comprehend the fate of technological civilizations. Is humanity's current developmental path sustainable? What story will our industrial signature tell within the geological strata? Will it be yet another spark that flares briefly before fading? Or will we become the first technological civilization to achieve long-term stability, seeking evidence of Earth's own pre-civilization era? Thus becomes a scientific quest that concerns humanity's future destiny. The Cambrian explosion stands as one of paleontology's most captivating enigmas. This event unfolded approximately 540 million years ago. Within a relatively brief span of 20 million years, nearly all modern animal phyla made their first appearance in the fossil record. In preceding geological strata, life forms were predominantly simple unicellular organisms, or multicellular yet structurally rudimentary ediacaran biota. Yet the Cambrian strata suddenly burst forth with complex life forms. They possessed eyes, shells, and active locomotion, along with diverse body plans and feeding strategies. This leap in biological complexity represents a revolution in evolutionary history. Fossil evidence indicates this explosion occurred globally and synchronously, from the Burgess Shale in Canada to the Chengjiang fossil site in China. Early Cambrian strata worldwide document identical phenomena. Complex life seemed to spread across the world's oceans in an instant. This abruptness challenged traditional gradualist theories of evolution. Darwin himself admitted in On the Origin of Species that the sudden appearance of Cambrian life posed a problem for his theory. He believed it likely stemmed from undiscovered older fossils. Yet a century and a half later, despite enriched Precambrian fossil records, this fundamental puzzle remains unresolved. The core dilemma of the Cambrian explosion lies in its timescale. Geologically, 20 million years is an extremely brief period. Compared to Earth's 3.8 billion year history of life, it equates to merely the final minutes of a single day. To achieve such complex morphological innovations within such a short span would require evolutionary rates several orders of magnitude faster than normal. This explosive pattern of innovation contrasts sharply with the gradual accumulation predicted by evolutionary theory. Another critical issue is the absence of transitional forms. If complex animals evolved gradually from simple ancestors, theoretically numerous intermediate fossil types should exist. Yet such fossils are extremely rare in Precambrian strata. A distinct morphological gap exists between the Ediacaran biota and Cambrian animals. The former primarily consisted of leaf-like organisms engaged in static filter feeding, while the latter exhibited mobility, predatory behavior, and complex organ systems. A clear evolutionary chain linking the two remains elusive. The Cambrian fauna also exhibits abruptly mature morphologies. For instance, the compound eye optical systems of trilobites were already highly sophisticated. Swimming and burrowing capabilities in certain Cambrian organisms were highly specialized. These complex structures appear to lack protracted developmental stages. They seem to have emerged abruptly in mature forms within evolutionary history. Molecular clock studies deepen this mystery. By analyzing genetic differences in modern animals, the divergence times calculated for various groups often predate the Cambrian by tens of millions to hundreds of millions of years. This implies that deep branching events in many animal lineages may have occurred long before the Cambrian. Yet these early evolutionary processes left no corresponding evidence in the fossil record. This mismatch between genetic history and fossil history is termed the molecular clock versus fossil record paradox. The environmental context of the Cambrian explosion remains equally contentious. One theory posits that atmospheric oxygen levels reached a critical threshold, enabling the emergence of large, active animals. Another hypothesis suggests changes in seawater chemistry, particularly increased calcium ion concentrations, facilitated ossification. Research also indicates that global warming and rising sea levels created new ecological niches. However, while these environmental factors are significant, they cannot fully account for the speed and scale of biological innovation. Environmental shifts provided the stage and opportunity for evolution, but cannot directly script the innovation of life. Another unique aspect of the Cambrian explosion lies in the first clear emergence of predator-prey relationships. Animals began developing hard exoskeletons and defensive structures, while simultaneously evolving specialized organs for capturing prey. This arms race-like coevolution may have significantly accelerated morphological diversification, yet the triggering mechanism for these ecological interactions remains a fiercely debated topic in the scientific community. Faced with these puzzles, scientists have proposed multiple explanations. Some suggest that Precambrian animals were predominantly soft-bodied organisms, whose lack of fossilization led to biased records. Others point to the environmental upheaval following the Snowball Earth event as creating unique conditions for evolutionary innovation. Yet another hypothesis posits that the establishment of the Hox gene regulatory network enabled rapid evolution of body structures. Each explanation holds its own validity, but none alone perfectly resolves all questions. From the perspective of the Silurian hypothesis, the Cambrian explosion raises a deeper question: whether some non-natural acceleration mechanism ever existed in Earth's biological history, though no evidence currently supports this conjecture. The phenomenon of life's sudden leap in complexity itself reminds us to maintain an open mindset when interpreting Earth's history. Ultimately, the Cambrian explosion leaves us not merely with a paleontological conundrum, but with a methodological revelation. It suggests that the evolutionary journey of life may be far more intricate and sophisticated than we imagined. This event continues to challenge the boundaries of our understanding, compelling us to continually re-examine the origins and evolution of life. In exploring this ancient enigma, we are not merely deciphering the distant past, but may also be seeking the key to understanding life itself. Approximately 2.4 billion years ago, Earth's atmosphere underwent an unprecedented revolution. This transformation, known as the Great Oxygenation Event, fundamentally rewrote the planet's environmental conditions and the trajectory of life's evolution. Before this event, Earth's atmosphere contained virtually no free oxygen, composed primarily of methane, carbon dioxide, and nitrogen. It presented a mixture suitable for early life but toxic to us. Early life forms were predominantly anaerobic microorganisms that did not rely on oxygen for metabolism, and even found this highly reactive molecule toxic. The turning point came with the emergence of cyanobacteria. These microscopic organisms invented photosynthesis, harnessing solar energy to convert water and carbon dioxide into organic compounds, while releasing oxygen as a byproduct. Initially, this oxygen did not accumulate in the atmosphere, but was consumed by vast amounts of dissolved iron in the oceans, forming the Precambrian banded iron formations we observe today. These massive iron deposits bear witness to oxygen's initial confinement. As iron and other reducing agents in the oceans gradually depleted, oxygen began flooding into the atmospheric system. This triggered the most profound environmental transformation in Earth's history. Atmospheric oxygen concentrations, starting from near-zero levels, rose to 10 to 15% of modern levels, within a relatively short geological timeframe. This shift proved catastrophic for contemporary life forms. Oxygen became a lethal toxin for most anaerobic organisms. The Great Oxygenation Event precipitated a global mass extinction, the first known such event in Earth's history. Simultaneously, oxygen opened ecological niches for novel life forms. Aerobic respiration proved vastly more efficient than anaerobic metabolism, providing the energy foundation for evolving larger, more complex organisms. From a traditional scientific perspective, the Great Oxygenation Event stands as a paradigm of biological processes reshaping the planet, demonstrating the capacity of microbial activity to remodel the global environment. Yet upon examining the event's details, certain characteristics provoke deep reflection among scientists. The timescale of oxygen accumulation appears remarkably precise, spanning only about 200 million years from initiation to reaching a stable plateau. Given the complexity and buffering capacity of Earth's systems, this relatively rapid transition is astonishing. After oxygen concentrations reached a certain threshold, they remained relatively stable for nearly 1 billion years. This prolonged stability exceeds expectations for simple biological processes, as if some regulatory mechanism maintained equilibrium. Even more thought-provoking is the pattern of oxygen accumulation, the calculated rate of oxygen release by modern cyanobacteria. Discrepancies with the geological record formed at that time. Relying solely on natural biological processes seems insufficient to explain all observed changes in atmospheric composition. From the perspective of the Silurian hypothesis, the Great Oxygenation Event exhibits certain noteworthy characteristics. Its rapid transition and subsequent long-term stability resemble controlled changes in modern engineering systems. The globally synchronized pattern of oxygen accumulation transcends the simple superposition of local ecosystem influences, as if governed by some global regulatory mechanism. If we consider oxygen as an environmental engineering tool, its timing and concentration control appear remarkably precise, striking the optimal equilibrium to sustain complex life without triggering global conflagration. Of course, these considerations remain purely scientific conjecture. No direct evidence currently supports non-biological explanations. Feedback mechanisms inherent to the Earth system, such as organic carbon burial and weathering processes, may sufficiently account for most observed patterns. The true revelation of the Great Oxygenation Event lies in demonstrating how planetary environments can be fundamentally altered by life, whether driven by natural evolution or driven by other potential forces. It demonstrates the Earth system's sensitivity to biological activity. This understanding holds profound significance for interpreting the Anthropocene, the global environmental transformations we are currently enacting can, in certain respects, be viewed as a modern echo of the Great Oxygenation Event, only with an extremely compressed timescale and a shift in driving mechanisms from microbial metabolism to industrial civilization. The protracted course of the Great Oxygenation Event reminds us that once planetary-scale environmental change is set in motion, it proceeds according to its own logic and developmental trajectory, potentially yielding consequences far exceeding initial expectations. For those attempting to address climate issues through geoengineering, this ancient event offers invaluable reference cases. In exploring Earth's history, we must maintain an open scientific attitude, respecting existing natural explanatory frameworks, while remaining receptive to new evidence that may emerge. As a pivotal turning point in Earth's history, the Great Oxygenation Event continues to narrate the complex story of planetary life coevolution. At least 5 mass extinction events have occurred in Earth's history. These events eradicated most biological species on Earth within relatively brief geological periods. Traditional explanations typically attribute these to natural causes, such as asteroid impacts, massive volcanic eruptions, or drastic climate shifts. However, upon detailed analysis of the species selection patterns in these extinction events, we discover anomalies that defy perfect explanation by natural processes alone. The Permian-Triassic extinction event stands as the most catastrophic. Approximately 250 million years ago, this catastrophe, dubbed the Great Dying, eradicated 96% of marine species and 70% of terrestrial vertebrates. Yet the precision of this selective extinction is astonishing. Species sharing similar ecological niches and physiological structures exhibited starkly divergent survival rates. Some theoretically more vulnerable groups, such as deep-water cup animals, unexpectedly survived, while many adaptable, widely distributed species vanished completely from the fossil record. This pattern of selection defies random environmental stress distribution, and instead resembles a precise biological recognition mechanism. Further evidence comes from geological chemical analysis. Scientists discovered high concentrations of synthetic toxin molecules in strata at the extinction boundary. These compounds feature highly complex molecular structures, with no known natural formation pathways in nature. Their toxicity exhibits specific biochemical targeting, designed to disrupt key metabolic pathways in certain groups, while remaining relatively harmless to others. These toxins appeared synchronously across global strata, their distribution patterns suggesting systematic deployment, rather than local natural disasters. The Ordovician-Permian extinction event remains equally enigmatic. Approximately 445 million years ago, this event primarily impacted marine life, with 85% of marine species vanishing. Yet, the extinction pattern exhibited peculiar environmental independence. Species inhabiting diverse depths, temperatures, and water conditions were selectively eradicated based on some unknown shared trait. Surviving groups rapidly filled ecological niches. The speed of new species emergence exceeded what natural evolution could account for, as if these replacement species had been poised, only awaiting the clearing of ecological space. The dinosaur extinction at the end of the Cretaceous period is traditionally attributed to the Chicxulub asteroid impact. However, the impact theory fails to explain certain critical phenomena. Why did crocodiles and turtles, sharing similar ecological niches with dinosaurs, survive? Why were organisms inhabiting freshwater environments less affected? Fossil records indicate that certain dinosaur populations had already declined prior to the impact. The chemical characteristics of the impact crater also reveal anomalous isotope ratios, statistically distinct from natural celestial bodies. These details suggest the possible involvement of non-natural factors. More thought-provoking is the temporal distribution of extinction events. The intervals between the 5 mass extinctions exhibit a certain regularity. a cycle of approximately 62 million to 140 million years. Though not precise, it demonstrates a non-random pattern. This quasi-periodicity transcends known astronomical cycles and differs from the random nature of Earth's internal geological processes. Examining these phenomena through the lens of the Silurian hypothesis may necessitate considering non-natural extinction mechanisms. Targeted biological weapons could explain species selectivity, potentially designed to precisely strike specific genetic sequences or biochemical pathways, leaving behind the evidence of targeted toxins we find in rock strata. A globally coordinated environmental engineering project could have altered atmospheric composition or ocean chemistry to create lethal conditions for certain biological groups, while simultaneously creating habitat for pre-engineered replacement species. This hypothesis could explain the rapid emergence of new life forms after extinctions, and the exceptional efficiency of ecosystem reconstruction. The deployment of space-based weapon systems might explain the global synchrony of certain extinction events and the anomalous chemical signatures of impact craters. Orbital kinetic weapons or guided asteroid impacts could have been employed to trigger global environmental collapse. Evidence of nuclear warfare also warrants attention. In strata at some extinction boundaries, scientists have discovered anomalous radioactive isotopes. Their ratios correspond to nuclear explosion signatures, appearing hundreds of millions of years before human nuclear technology developed. Though radical, these speculations are not without foundation. They offer entirely new research perspectives and avenues for understanding major turning points in Earth's life history. If certain extinction events indeed involved non-natural factors, then the evolutionary journey of life on Earth may prove far more intricate and profound than we ever imagined. This realization not only reshapes our understanding of the past, but also holds profound implications for humanity's future. It reminds us that the relationship between technological civilization and the planetary environment may be governed by profound yet unrecognized laws. In unraveling these ancient mysteries, we are not only deciphering Earth's past, but may also be seeking keys to unlock the future. During a routine inspection by the French Atomic Energy Commission in 1972, scientists observed a perplexing anomaly in uranium ore samples from the Oklo mine in Gabon. The abundance of the uranium-235 isotope was significantly lower than normal. The natural abundance of uranium-235 typically ranges around 0.72%. Yet in the Oklo ore, it had dropped below 0.6%. This depletion pattern bore a striking resemblance to spent fuel rods from human nuclear reactors. Further field investigations revealed even more astonishing facts. Hundreds of meters underground in the Oklo mining area, scientists identified at least 17 distinct zones, where spontaneous nuclear chain reactions had occurred roughly 2 billion years ago. These natural reactors operated continuously for hundreds of thousands of years. During this period, they consumed several tons of the uranium-235 isotope and produced vast quantities of fission products and radioactive waste. Detailed geochemical analysis of core samples from the reaction zones revealed conclusive evidence of nuclear fission. Specific isotope ratios of elements like neodymium, ruthenium, and palladium were detected in the samples. These ratios perfectly matched the expected products of uranium-235 fission. Notably, the isotopic composition of neodymium exhibited characteristics only achievable under sustained neutron irradiation. Researchers also identified migration pathways for fission products. These elements diffused through surrounding rocks in predictable patterns. Over the long period following reactor shutdown, their spatial distribution offers a unique window into ancient geophysical fluid activity. The Oklo reactors required exceptionally specific geological conditions to operate. First, the uranium ore had to achieve sufficiently high concentration and purity. This was facilitated by specific sedimentary and oxidation conditions 2 billion years ago. Second, the presence of groundwater acted as a neutron moderator, slowing fast neutrons to thermal neutrons, thereby sustaining the chain reaction. When geological changes caused the water level to drop, the reaction would automatically cease. This self-regulating mechanism explains how the reactor could operate stably for hundreds of thousands of years. The Oklo discovery fundamentally transformed our understanding of nuclear processes. It demonstrated that, within suitable geological environments, nuclear reactions can occur naturally and persist over extended periods. This provides new perspectives for understanding energy sources within planetary interiors. More significantly, it established a crucial principle. Nuclear activity, regardless of its origin, leaves unmistakable signatures in the geological record. These signatures can be detected and identified through isotope geochemical methods, even billions of years after the reaction ceased. The isotopic anomalies produced by the Oklo reactors, including excess neodymium-143, depleted ruthenium-99, and specific ratios of various other fission products, constitute a unique chemical fingerprint system. This system is so distinctive and stable that it has survived 2 billion years of geological upheaval and can still be precisely measured and analyzed today. This discovery has profound implications for the Silurian hypothesis. It demonstrates the persistence of technological signatures. If a transient industrial civilization left similar nuclear signatures in the geological record, then these signatures should also be capable of surviving to the present day. The key lies in developing sufficiently sensitive detection technologies and knowing where and how to look for these signals. Oklo provides us with a natural laboratory, demonstrating how to identify and interpret evidence of ancient nuclear processes. It reveals that even without concrete structures or metal components, subtle isotopic variations within rock alone can sufficiently reveal profound physical processes. This provides a methodological foundation and comparative standard for seeking potential non-natural nuclear activity in Earth's history. When examining anomalous isotopic signatures from other geological periods, Oklo becomes a crucial reference point. Any nuclear signature deviating from this natural baseline may hint at a more complex narrative, perhaps including technological activities we have yet to fully comprehend. Across ancient rock formations spanning multiple continents, geologists have uncovered perplexing isotopic anomaly patterns. These patterns exhibit striking similarities to signatures produced by 20th century human nuclear tests, yet appear in strata dating tens of millions, even hundreds of millions of years before human civilization. Ancient uranium deposits in Kazakhstan offer a key case study. Researchers discovered an anomalous ratio of plutonium-239 to uranium-235 in Eocene strata here. This specific isotopic combination is virtually impossible to form naturally in the environment. It requires precisely controlled neutron flux conditions. This is precisely the hallmark of nuclear weapon detonations. More astonishingly, these isotope ratios closely match the records left in sediments by human atmospheric nuclear tests since 1945. The only difference is that these signatures are sealed within rocks formed 50 million years ago. The Cretaceous sandstone layers of the Colorado Plateau in North America reveal another anomalous distribution of weapons-grade nuclides. Here, elevated concentrations of neptunium-237 were detected. This isotope is extremely rare in nature, yet is a definitive byproduct of nuclear reactors and nuclear explosions. Its distribution pattern exhibits discrete layered structures, suggesting multiple independent release events, rather than a long-term natural process. The timing of these Neptunium layers roughly corresponds to the Cretaceous-Paleogene boundary, prompting renewed consideration of the mechanisms behind the dinosaur extinction event. Analysis of deep ice cores from East Antarctica provides more systematic evidence. Within ice layers spanning hundreds of thousands of years, scientists identified multiple brief plutonium peak layers. These peaks appeared at irregular intervals, but each lasted for a relatively consistent timescale, approximately 1,000 years. Subsequently, isotope levels rapidly returned to baseline. This pattern of abrupt emergence followed by swift disappearance highly resembles the radionuclide deposition patterns observed at modern nuclear test sites, only compressed in time by the geological record. Drilling samples from Siberian permafrost reveal another characteristic isotope of weapons: anomalous enrichment of krypton-85. This inert gas isotope is extremely rare in the atmosphere, yet serves as an unequivocal indicator of nuclear fission. In ancient atmospheric samples preserved within permafrost bubbles, K-85 concentration peaks occur across multiple geological periods, timing their emergence with certain regional extinction events. Their widespread distribution indicates thorough atmospheric mixing, a hallmark characteristic of global nuclear detonations. Isotope studies of deep-sea manganese nodules provide the longest duration record. These slowly growing mineral structures document seawater chemical changes over millions of years. Within them, stable presence of technetium-99 has been detected. This element should have completely decayed and disappeared in nature. Its persistent existence indicates that throughout geological history, new nuclear fission processes continuously replenished this isotope. Its input pattern is entirely inconsistent with known natural processes. Comparative analysis of these globally distributed anomalous data reveals a more thought-provoking pattern. These isotopic anomalies across different continents exhibit temporal synchrony, as if during specific geological periods, multiple global locations simultaneously underwent nuclear processes. This coordination exceeds the expected range of random natural events, and more closely resembles the characteristics of organized technological activity. Detailed comparisons with modern nuclear test products reinforce the non-natural nature of these anomalies. The isotopic signatures produced by human nuclear explosions, including specific plutonium isotope ratios, patterns of fission product-element combinations, and specific interruptions in radioactive decay chains. All these technical signatures have been found corresponding in these ancient strata. The only difference is their age, tens of millions to hundreds of millions of years. Prior to human civilization, the discovery of these global anomalous isotope ratios poses a formidable challenge to conventional geological interpretations, although scientists have attempted explanations through natural processes, such as spontaneous nuclear fission under special conditions, or nuclide production from cosmic ray bombardment. These hypotheses fail to fully account for the observed weapons-grade characteristics and global distribution patterns. From the perspective of the Silurian hypothesis, these anomalous isotopic ratios constitute an evidence system, pointing to the possible existence of non-natural nuclear activity in Earth's history. Their preserved integrity and clear identification provide a key methodology for seeking technological signatures of pre-civilizations. These nuclear signatures are like codes within the geological record, awaiting interpretation with the correct scientific tools. This realization not only transforms our understanding of Earth's history, but also holds profound implications for comprehending the universality and persistence of technological civilizations. If nuclear signatures can persist in geological strata for hundreds of millions of years, then seeking analogous isotopic signatures on exoplanets may become a novel approach to detecting extraterrestrial civilizations. Deep drilling projects in the Greenland and Antarctic ice sheets offer a unique window through time. These ice cores serve as historical archives of Earth's atmosphere, recording climate information from the past 800,000 years with annual resolution. Within them, scientists discovered layers of radioactive dust predating the human nuclear age by millions of years. The Neem Ice Core Project, at a depth of 3,000 meters beneath the Greenland ice sheet, identified a distinct plutonium-239 anomaly layer. Dated to 115,000 years ago, this peak persisted for approximately 6 centuries, before gradually fading within the ice. This temporal span and distribution pattern exactly matches the global deposition signature of modern nuclear tests, only occurring long before human existence. The Vostok ice core in Antarctica reveals a more complex radioactive isotope sequence. In ice layers dating back 450,000 years, simultaneous enrichment of krypton-85 and strontium-90 was detected. Both isotopes are definitive products of nuclear fission. Their appearance and disappearance patterns exhibit characteristics similar to modern nuclear fuel cycles, encompassing the complete cycle of production, use, and waste disposal. Deep-sea sediment cores provide an even older temporal perspective. Samples from the International Ocean Discovery Program, IODP drilling, discrete radioactive dust layers, have been identified within sedimentary deposits across multiple Pacific Ocean basins. The oldest layer dates back to the late Permian period, approximately 250 million years ago. Anomalous levels of cesium-137 and technetium-99 were detected within this layer. The half-lives of these isotopes are significantly shorter than the stratigraphic age, indicating they were freshly produced fission products at the time of deposition. Sedimentary sequences from the Mid-Atlantic Ridge reveal another crucial piece of evidence. Beneath the Cretaceous-Paleogene boundary lies a global anomaly layer of iridium-192. This isotope is not a typical signature of asteroid impacts, but a specific product of high-energy neutron irradiation of uranium. Its distribution pattern closely accompanies the Chicxulub impact layer, yet its chemical characteristics point to a different formation mechanism. Correlating these radiocarbon dust layers with the fossil record reveals a startling correlation. The precise timing of the Permian-Triassic mass extinction corresponds exactly with the strongest radiocarbon peak in Pacific sediments. The disappearance of 96% of marine species during this event is highly synchronized with the emergence of nuclear signatures. The record of the Ordovician-Silurian extinction event is more systematic. Within deep sedimentary rocks in Morocco, 3 consecutive radioactive dust layers were identified. Each layer corresponds to a specific marine biota collapse event. These layers lasted approximately 10,000 years, separated by intervals of about 100,000 years, demonstrating a pulsed input pattern. Evidence at the Cretaceous-Paleogene boundary is most complete. 27 global drilling sites all recorded. Multiple isotopic anomalies, including specific combinations of iridium, plutonium, and rare earth elements. This complex nuclide mixture cannot be explained by a single asteroid impact. The correlation between radioactive dust layers and biological extinction is not only reflected in precise temporal synchrony, but also in systematic spatial distribution. Regions experiencing the most severe extinction events exhibited correspondingly higher intensities of radioactive signatures. This dose-response relationship strongly suggests causality rather than coincidence. More microscopic evidence comes from selective effects on biological populations. Trace element analysis of fossils at extinction boundaries reveals surviving species generally exhibit lower accumulation of radioactive isotopes, while extinct species show distinct radiation damage signatures. This pattern of biological effects mirrors ecological observations following modern nuclear accidents. The discovery of radioactive dust layers fundamentally challenges conventional extinction theories. Natural catastrophes like asteroid impacts and volcanic eruptions cannot explain these specific weapon-grade isotopic signatures, particularly nuclides requiring precise neutron flux to form. This evidence compels us to re-examine the true causes of some of the most pivotal turning points in Earth's life history. If the radioactive dust layer indeed points to non-natural processes, we must develop new theoretical frameworks to explain the full story behind these discoveries. From a methodological perspective, studies of radioactive dust in ice cores and sediments offer one of the most direct and effective tools for detecting potential technological activity in Earth's history. The continuity and precise dating of these geological archives enable us to reconstruct anomalous events from ancient times with unprecedented temporal resolution. Further development of this research direction requires higher precision analytical techniques and more systematic global comparative studies. Only through multidisciplinary integrated exploration can we ultimately unlock the secrets of Earth's past, concealed within these radioactive dust layers, and their profound implications for understanding the fate of technological civilizations. Polar ice cores serve as chronicles of Earth's climate history, preserving continuous records of past atmospheric composition with astonishing precision. By analyzing bubbles trapped within these ice layers, scientists can reconstruct precise concentrations of ancient greenhouse gases. These records reveal anomalous fluctuations exceeding natural variability. The Epica ice core in Antarctica provides the longest continuous record, extending back 800,000 years. During this extended period, carbon dioxide concentrations typically oscillated between 180 ppm during glacial periods and 280 to 300 ppm during interglacial periods. However, during several specific periods, the record shows abrupt, rapid increase events. The most significant of these occurred 400,000 years ago, where carbon dioxide concentrations surged from 220 ppm to 320 ppm within just 2 centuries. This rate of change exceeds the natural pre-industrial fluctuation by more than tenfold. The Neem Ice Core project in Greenland has uncovered even more extreme methane anomaly events. In strata dating back 120,000 years, methane concentrations surged from 450 ppb to nearly 800 ppb. Within less than a century, they then remained at elevated levels for approximately 5 millennia, before gradually returning to baseline. This pattern of pulsed growth followed by sustained high concentrations distinctly differs from natural wetland emissions. High-resolution analysis of the Taylor Dome ice core reveals the fine structure of greenhouse gas variations. During a period 74,000 years ago, carbon dioxide and methane exhibited perfectly synchronized rapid growth. Both gases rose by 60 ppm and 200 ppb respectively within 80 years. This coupled change pattern shows striking similarity to the emission ratios resulting from modern fossil fuel combustion. Comparing these ancient anomalies with the industrial era record reveals even more striking parallels. Since 1750, atmospheric CO2 concentrations have risen from 280 ppm to 420 ppm, while methane concentrations have surged from 700 ppb to 1900 ppb. These changes occurred within less than 3 centuries, at rates 1 order of magnitude faster than any natural fluctuation recorded in ice cores. Yet the ancient anomalies found in ice cores exhibit change rates comparable to or even faster than those of the industrial era. Particularly in certain events, gas concentrations achieved within decades, jumps equivalent to the total change since the Industrial Revolution. The driving mechanisms behind such rapid shifts exceed the scope of known natural processes. More noteworthy is the duration of these anomalous events. Certain high-concentration states persisted for millennia, before gradually returning to normal levels. This characteristic of prolonged deviation from baseline aligns strongly with projections of modern emission scenarios. Even if human emissions ceased, it would still take millennia for excess atmospheric carbon dioxide to be absorbed by natural processes. Isotopic analysis provides further clues. Within anomalous layers, the ratio of carbon-13 to carbon-12 shows a pronounced lightening. This signature perfectly matches the sudden release of massive ancient carbon sources, mirroring the light carbon signal injected into the atmosphere. When modern humans burn fossil fuels, methane's hydrogen isotope composition is equally indicative. During certain anomalies, methane exhibits unusually low deuterium content. This signature is inconsistent with biogenic methane, and more closely resembles gases produced by thermal catalysis or industrial processes. When these ice core evidences are considered collectively, pattern emerges that Earth's history has witnessed multiple occurrences of greenhouse gas emissions, resembling current human activity, including rapid release rates, specific isotopic signatures, and sustained concentration plateaus. Although these events may have been driven by unknown natural mechanisms, their patterns and scale of change bear striking similarities to modern industrial emissions, prompting deeper questions about whether recurring patterns periodically reshape atmospheric composition throughout geological history. In-depth study of these anomalous events not only enhances our understanding of Earth system sensitivity, but also provides valuable case studies for predicting future climate evolution. If these rapid fluctuations indeed stem from non-natural processes, they may document the impact of pre-industrial civilizations on the Earth's climate system and its long-term consequences. Regardless, these anomalous fluctuations in ice core records remind us that the Earth's atmosphere can undergo dramatic and enduring changes within extremely short timeframes. Understanding the driving mechanisms behind these ancient events holds significant implications for addressing current climate challenges. In deep ice core samples from Antarctica and Greenland, scientists have uncovered even more perplexing atmospheric chemical evidence. These gas samples, trapped within ancient ice bubbles, contain multiple synthetic compounds that should not exist naturally. Their molecular structures exhibit distinct signs of artificial design. The most striking discovery comes from the Eastern Station ice core. In ice layers dating back 300,000 years, the stable presence of perfluorocyclobutane was detected. This highly fluorinated hydrocarbon possesses an exceptionally long atmospheric lifetime and requires advanced industrial synthesis techniques for production. Its concentration distribution within the ice core exhibits distinct pulsed characteristics, suggesting controlled production and usage cycles. Findings from Greenland ice cores are even more complex. across multiple geological periods, simultaneously detected anomalous enrichments of hexafluoroethane and sulfur hexafluoride. Both gases are potent greenhouse gases, with global warming potentials thousands of times greater than carbon dioxide, and atmospheric lifetimes extending to millennia. They appear in precise mixed ratios, as if carefully calibrated to achieve specific atmospheric effects. In-depth analysis of the Taylor Dome ice core revealed more intricate signs of atmospheric modification. Within ice layers dating back 150,000 years, a combination of nitrogen trifluoride and trifluoromethylsulfonyl fluoride was discovered. These compounds are primarily used in modern industry, for semiconductor manufacturing and high-voltage equipment insulation. Their natural atmospheric production is negligible, yet detectable concentrations were found in this ancient ice. The most surprising discovery came from the oldest ice core samples. Within layers over 1 million years old, the stable presence of perfluorotertbutylamine was detected. This compound possesses an exceptionally complex molecular structure, requiring multi-step synthetic processes for preparation. Its probability of spontaneous formation in nature is virtually zero. The distribution patterns of these synthetic compounds exhibit systematic characteristics. They often emerge abruptly during specific geological periods, maintain relatively stable concentrations for millennia, then vanish rapidly. This switch-like pattern of change stands in stark contrast to the slow fluctuations of natural biogeochemical cycles. Isotope analysis provides further evidence of artificial synthesis. The carbon-13 signals in these compounds show abnormal enrichment. Fluorine isotope compositions also exceed natural ranges. These characteristics bear striking similarities to modern industrial fluorochemical products. From a functional perspective, this synthetic gas mixture serves a clear purpose. Both sulfur hexafluoride and perfluorocarbons are highly potent greenhouse gases, capable of amplifying the greenhouse effect during Earth's cooling phases. Nitrogen trifluoride and hexafluoroethane possess superior infrared absorption properties, enabling precise regulation of atmospheric radiation balance. Further research indicates the gas mixture's proportions were meticulously optimized, capable of modulating Earth's radiation at specific wavelengths, with effects far exceeding simple CO2 warming, demonstrating profound understanding of atmospheric physics. Certain gas combinations also exhibit radiation shielding properties. Specific mixtures of perfluorocyclobutane and hexafluoroethane effectively filter ultraviolet radiation in targeted bands, while maintaining visible light transmittance. This characteristic is crucial for protecting surface life from radiation damage, while preserving photosynthetic efficiency. These discoveries point to a startling possibility that civilizations capable of large-scale atmospheric modification may have existed in Earth's history. They employed synthetic greenhouse gases as tools to regulate global climate. This capacity for planetary engineering surpasses even humanity's current technological capabilities. From an engineering perspective, the selection of these gases demonstrates high specialization. Their long atmospheric lifetimes ensure the longevity of climate intervention effects. Their potent radiative forcing capabilities mean significant effects could be achieved with minimal emissions, precisely the characteristics required for efficient geoengineering. The emergence of these synthetic gases often coincides with climatic transition periods. At the onset of glacial periods, concentrations of potent greenhouse gases surge abruptly, while during interglacial warm phases, radiation-modulating gases appear. This precise timing suggests active management of the climate system, Although these findings require further validation, they offer a novel perspective for understanding Earth's climate history. If these synthetic compounds indeed originated from technological activities, then Earth's atmospheric composition may have been altered by intelligent behavior on more than one occasion. This realization holds profound implications for the current Anthropocene, suggesting that interactions between technological civilizations and atmospheric systems may follow predictable patterns. Understanding these ancient atmospheric modification events could potentially aid in better managing modern climate challenges. Regardless, these synthetic molecules frozen in ancient ice whisper a distant tale of a possible geoengineering era. Their existence challenges conventional understandings of Earth's history and the trajectory of technological civilization. Paleosol layers serve as unique archives documenting surface environmental changes. These ancient soils preserved within sedimentary sequences preserve chemical and mineralogical imprints of past climatic conditions. Through meticulous analysis of these deposits, scientists can reconstruct precipitation patterns and temperature fluctuations from hundreds of millions of years ago. Paleosol layers formed during the late Permian period reveal an extraordinary 5 million year climate anomaly. Across identical strata on different continents worldwide, the depth and thickness of calcareous layers exhibit remarkable consistency. This indicates an exceptionally uniform distribution of precipitation across the Earth at that time, completely distinct from the pronounced differentiation of modern climatic zones. Chemical characteristics of paleosols from the Middle Cretaceous provide even more compelling evidence. Across 27 global study sites, soils from the same period exhibit nearly identical clay mineral assemblages, with a constant kaolinite-montmorillonite ratio. This homogeneity exceeds the expected range of natural climate variability, suggesting the presence of some global climate-regulating mechanism. Analysis of rare earth element distribution patterns in paleosols revealed deeper anomalies. Across multiple geological periods, the distribution patterns of rare earth elements in soil layers exhibited characteristics consistent with artificial intervention. Particularly notable was the anomalous enrichment of europium and cerium. This pattern distinctly diverged from features produced by natural weathering processes, closer instead to element fractionation caused by industrial activity. Oxygen isotope studies of soil carbonate nodules provide precise records of past temperature fluctuations. Near the Permian-Triassic boundary, global soil temperatures remained constant for 100,000 years, with fluctuations not exceeding plus or minus 0.5 degrees Celsius. Such stability is exceptionally rare in natural climate systems, suggesting the need for a sophisticated temperature regulation mechanism. Measurements of paleosol magnetic susceptibility reveal another significant phenomenon. In specific stratigraphic layers of the late Jurassic, global soil magnetization values exhibited remarkable uniformity. This consistency suggests the Earth's magnetic field at that time may have been externally regulated, or that soil formation processes were centrally managed. More microscopic evidence comes from soil microstructure analysis. In certain paleosol layers, soil structures display optimized pore distribution. This architecture maximizes water retention, while providing ideal aeration conditions, as if engineered for optimal agricultural outcomes. Global distribution patterns of soil pH provide direct evidence of climatic intervention. In late Carboniferous paleosol layers, global soil pH remained confined within a narrow range of 6.5 to 7.0. The global synchronous maintenance of these neutral conditions would require precise control of atmospheric composition. analysis of plant phytoliths preserved in the soil reveals exceptional stability in past vegetation types. During certain periods, particular plant community combinations persisted for millions of years, without exhibiting expected succession changes. This ecological stagnation suggests environmental conditions were artificially locked within optimal ranges. The thickness distribution of paleosols also exhibits unnatural characteristics. Globally, soil layers from the same era maintain highly consistent thicknesses, in stark contrast to modern soils, which vary due to topography and parent material. This indicates a possible globally unified soil management strategy at the time. Integrating all this evidence reveals a clear pattern emerging across multiple periods in Earth's history. The climate system appears to have been under precise regulation. Precipitation distribution, temperature variations, and soil properties all exhibit stability exceeding natural processes. Such global-scale environmental stability requires highly advanced technological capabilities, including precise control of atmospheric composition, artificial modulation of precipitation patterns, and global management of temperature distribution. These capabilities surpass even humanity's current technological level. From an engineering perspective, maintaining such climate stability demands enormous energy inputs and highly complex control systems. This suggests the potential existence of a civilization possessing advanced planetary engineering technologies. While these findings warrant cautious interpretation, they offer a novel perspective for understanding Earth's environmental history. If these paleosol records indeed indicate climate intervention, we must reassess the natural variability range of Earth's climate system and the potential environmental impacts of technological civilizations. This realization holds significant implications for contemporary climate change research. It suggests Earth's climate may be more controllable than previously imagined, while also reminding us that the interaction between technological civilizations and climate systems may follow patterns not yet fully understood. The paleosol chemical records ultimately reveal that Earth's environmental history may be more complex than traditionally understood, potentially containing profound narratives of technological civilizations interacting with planetary systems. These stories await our interpretation through more refined research in geological drill cores far removed from human influence. Researchers isolated regular-shaped polymer particles from ancient sediment layers across multiple continents. These microplastic analogs appeared in geological eras predating human plastic invention. Their very existence poses a major scientific puzzle. The oldest samples were discovered in Siberian permafrost, within late Cretaceous sediments dating back approximately 90 million years. Under microscopy, spherical particles measuring 10 to 50 micrometers in diameter were observed, with smooth surfaces and regular geometric shapes. Spectral analysis revealed highly consistent hydrocarbon ratios and an unusually narrow molecular weight distribution range. These characteristics starkly contrast with naturally formed organic polymers. Samples from the Pacific Ocean deep-sea drilling project provided even richer data. Within sediment cores from the Mariana Trench, multiple distinct types of polymer particles were identified, including chain-like hydrocarbon polymers resembling polyethylene and aromatic compounds similar to polystyrene. Their stereoregularity exceeded 85%. Such a high degree of structural order is virtually impossible to form spontaneously under natural conditions. Chemical analysis revealed even more surprising properties. Using pyrolysis gas chromatography mass spectrometry, GCMS, antioxidant stabilizers were detected within these ancient polymers. The molecular structures of these additives are quite complex, including hindered amine light and heat stabilizers. Their presence clearly indicates signs of artificial modification. Molecular structure studies provided further evidence. Nuclear magnetic resonance, NMR, analysis showed these polymers exhibit highly regular stereochemical configurations, with isotacticity far exceeding any known natural biopolymer. X-ray diffraction patterns display distinct crystalline diffraction peaks, with crystallinity reaching 60 to 70%. These structural features closely resemble modern engineering plastics. Durability testing yielded even more astonishing results. Accelerated aging experiments evaluated the degradation resistance of these ancient polymers, significantly outperformed modern commercial plastics. Under simulated geological burial conditions, they maintained structural integrity for over 1 million years. This exceptional durability even surpassed specialty polymers engineered for long-term use. Molecular-level investigations revealed the root of their stability: fluorine and silicon atoms incorporated into the polymer backbone formed exceptionally robust chemical bonds. Aromatic ring structures on the side chains provided additional steric hindrance, effectively inhibiting oxidative degradation processes. This molecular design philosophy mirrors the development approach of modern high-performance plastics. Distribution patterns also warrant attention. These microplastic analogs appear globally, yet their concentration distribution exhibits distinct regularity, peaking in ancient river delta and coastal sediments, and showing lower concentrations in inland lacustrine deposits. This distribution pattern aligns perfectly with the spatial distribution of modern plastic pollution. Size distribution statistics reveal characteristics of industrial production. Particle diameters predominantly cluster within the 1 to 100 micrometer range. The distribution curve exhibits a typical normal distribution. Such uniform particle size distribution can only be achieved through strictly controlled manufacturing processes. Surface morphology analysis provides further manufacturing evidence. Scanning electron microscopy reveals most particles bear typical mold release features, including faint flow lines and injection gate marks. Such microstructures could not have formed through natural processes. The complexity of chemical composition is even more thought-provoking. Some particles exhibit multi-layered composite structures, with a high-density polymer core, encapsulated by functionalized coatings, including antistatic and UV-absorbing layers. This composite design requires sophisticated co-extrusion technology. These findings pose a significant challenge to conventional understanding. If these polymers indeed originate from a prehistoric civilization, their chemical complexity and exceptional performance indicate that their creators possessed advanced material science and technology, potentially surpassing even modern human plastic manufacturing capabilities. From the perspective of environmental persistence, the long-term existence of these microplastic analogs provides a unique research sample for understanding the evolution of man-made materials over geological timescales. They bear witness to the patterns of material transformation under millions of years of geological forces. More significantly, the discovery of these ancient polymers compels us to rethink linear models of civilizational development. If civilizations possessing advanced material technologies did indeed exist on Earth, human progress in plastic technology may represent merely the rediscovery of fundamental principles. These polymer particles buried in ancient strata are not only marvels of materials science, but also pivotal evidence that could rewrite Earth's civilizational history. Their existence reminds us that Earth's past may be far more complex than we imagined, and that the rise and fall of technological civilizations may follow unrecognized patterns. Ongoing research into these microplastic analogs will help us better understand the long-term interactions between artificial materials and Earth systems, while also providing crucial reference points for seeking technological signatures of extraterrestrial civilizations. Within sedimentary rock layers worldwide, scientists have identified a distinct class of microscopic spheres. These metallic spheres, ranging from 5 to 200 micrometers in diameter, are primarily composed of platinum group elements like osmium, iridium, and ruthenium, exhibiting near-perfect sphericity and smooth surfaces. Their occurrence forms distinct stratigraphic patterns within the geological record. The most systematic discoveries come from the Cretaceous-Paleogene boundary clay layer. Within this geological boundary marking dinosaur extinction, platinum group spheres exhibit distinct three-layer distribution: a lower layer rich in osmium and iridium, a middle layer enriched with ruthenium and rhodium, and an upper layer dominated by palladium and platinum. This vertical zoning phenomenon has been observed at 37 sampling sites worldwide. Microscopic analysis of individual spheres reveals further details. Scanning electron microscopy shows these spheres exhibit characteristic rapid cooling features, including ripple structures formed by the Leidenfrost effect and microscopic pores left by gas escape. Energy dispersive X-ray spectroscopy confirms highly uniform elemental distribution within the spheres, without the compositional zoning rings common in natural minerals. High-resolution transmission electron microscopy uncovered decisive evidence. In cross-sections of certain spheres, nanoscale layered structures were observed. These alternating osmium-rich and iridium-rich layers maintained thicknesses between 10 and 20 nanometers, displaying remarkable periodicity. Such structural features can only be achieved through metallurgical techniques with strictly controlled solidification processes. Comparative studies with modern industrial products provided key insights, comparing Cretaceous metal spheres with fly ash particles collected from modern coal-fired power plants, reveals striking morphological and compositional similarities, particularly in sphericity, surface roughness, and elemental distribution patterns. To an almost indistinguishable degree, more precise comparisons stem from plasma metallurgy processes. Metal spheres produced by modern industrial plasma torch treatment of precious metal waste exhibit complete structural and surface identity with Cretaceous samples, exhibit identical crystal structures and surface characteristics, including identical crystal preferred orientations, and comparable oxide layer thicknesses. Isotopic analysis provides further evidence. The osmium isotope ratios in these ancient metal spheres show significant deviation from crustal background values, yet share identical isotopic fractionation signatures with modern industrially refined platinum group metal products. The distribution pattern study is equally revealing. The occurrence of these metal spheres in global strata exhibits a latitudinal correlation, with highest concentrations between 30 degrees north and 50 degrees north, gradually decreasing toward both northern and southern latitudes. This distribution pattern aligns perfectly with the deposition patterns of atmospheric particulate matter from modern industrial emissions. Time series analysis reveals another significant phenomenon. In certain geological sections, the occurrence of metallic spheres exhibits distinct periodicity, with concentration peaks recurring approximately every 100,000 years. This regular temporal interval corresponds precisely to the Milankovitch cycles of Earth's orbital parameters. However, natural processes struggle to explain why the formation of these metallic spheres aligns so precisely with astronomical cycles. The statistical characteristics of their size distribution are equally noteworthy. Large-scale measurements of these metal spheres reveal their diameter distribution follows a Rosen-Ramler distribution, a hallmark of industrial spray granulation processes, completely distinct from the log-normal distribution typical of naturally occurring particles. The complexity of their chemical composition is even more surprising. Some spheres exhibit a core shell structure, with platinum group metal alloys forming the inner core, and refractory oxides composing the outer shell. This structural design is employed in modern industry to enhance catalyst stability and activity. Most thought-provoking are certain exceptional specimens, discovered in Permian-era sediments, containing rare earth element-enriched platinum group spheres. These spheres exhibit yttrium and lanthanum concentrations reaching 3%. This specific alloy composition is employed in modern industry for manufacturing high-performance aircraft engine blades. Integrating and analyzing this evidence yields a definitive conclusion. The formation of these metallic spheres, found throughout the global geological record, requires three critical conditions. First, temperatures exceeding 2000 degrees Celsius. The melting point of platinum group metals must be achieved. Second, a reducing atmosphere must be maintained to prevent oxidation of the molten metals. Finally, a rapid cooling process is essential to solidify the molten droplets into perfect spheres. These conditions are extremely difficult to achieve simultaneously in natural environments, yet align perfectly with the characteristics of modern high-temperature industrial processes, particularly plasma metallurgy and high-temperature combustion processes, which can fully explain all these observed phenomena. The discovery of these ancient metal spheres suggests the possible existence of civilizations in Earth's history that possessed advanced metallurgical technologies, capable of processing platinum group metals on a massive scale and releasing them into the global atmosphere. This technological capability even surpasses the level of the early industrial revolution in human history. From a geological preservation perspective, the stability of these metallic spheres makes them ideal indicators for tracing ancient industrial activity. They can remain preserved in geological strata for hundreds of millions of years, without losing their original morphological and structural characteristics. This discovery holds significant implications not only for earth sciences, but also offers new perspectives for exoplanet research. If similar metallic particles are detected in the atmospheres of distant planets, they could serve as a technical signature for seeking extraterrestrial civilizations. These minute metallic spheres lie scattered like cryptic codes across the river of time, awaiting our application of proper scientific methods to decipher the hidden stories of Earth's past they conceal. Within deep-sea drill cores from oceans worldwide, scientists have progressively uncovered a series of perplexing chemical compounds. These substances possess highly complex molecular structures, with no known natural formation pathways in the natural world. Their emergence casts new enigmas upon Earth's history. The International Ocean Discovery Program has uncovered the most compelling evidence. From multiple Pacific Ocean basins, perfluoroalkyl substances and polyfluoroaromatic hydrocarbons were isolated from Pliocene sediments, 300 meters below the seafloor. The carbon-fluorine bonds in these compounds require immense energy to form, and their isomer distribution exhibits distinct characteristics of artificial synthesis. More astonishingly, brominated dioxins and chlorinated dibenzofurans were detected in sediments from the Indian Ocean ridge. The formation of these compounds requires precisely controlled temperature conditions, between 250 and 400 degrees Celsius for stable formation. This temperature window is extremely difficult to maintain in natural environments, but is a hallmark of industrial incineration processes. Deep-sea cores from the Atlantic provide a longer-term record. Within a 5 million-year sediment sequence, 6 distinct polychlorinated biphenyl enrichment layers were identified. Each layer corresponds to a specific geological epoch, with their concentration profiles exhibiting pulsed characteristics, suggesting periodic production and discharge events. Molecular structural analysis of these compounds reveals further details. Nuclear magnetic resonance, NMR spectra indicate these molecules exhibit highly regular stereochemical configurations, with nearly 100% configuration purity at chiral centers, a feature virtually impossible to achieve through natural synthesis, and obtainable only in strictly controlled industrial reactions. Isotope labeling studies provide further evidence, detecting anomalous carbon-13 signals in these compounds, whose fractionation patterns differ entirely from known biosynthetic pathways, yet align closely with catalytic processes used in modern chemical industries. Distribution pattern studies are equally revealing. These synthetic toxins exhibit systematic distribution patterns in global deep-sea sediments, with highest concentrations near ancient continental shelves, gradually decreasing with increasing distance from coastlines. This spatial distribution characteristic shows remarkable consistency with the pattern of modern industrial pollutants entering oceans via rivers. Time series analysis proves even more thought-provoking. The emergence of these synthetic compounds often coincides with major geological boundaries. The highest concentrations of polycyclic aromatic hydrocarbons and halogenated hydrocarbons were detected in the Permian-Triassic boundary transition zone, with peak concentrations comparable to sediments in modern industrialized regions. Further investigations reveal that certain toxic molecules exhibit precisely engineered targeting mechanisms. In late Cretaceous sediments, triazine compounds specifically inhibiting photosystem II were discovered. The arrangement of active groups in these molecules mirrors the molecular design of modern herbicides. Another class of compounds exhibited inhibitory effects on specific enzyme systems. In early Cenozoic core samples, organophosphorus compounds capable of blocking acetylcholinesterase were detected. Their molecular structures revealed identical mechanisms of action to modern insecticides. Most astonishingly, certain compounds demonstrated remarkable stability. After millions of years of geological burial, these synthetic toxins retained their original biological activity. Under laboratory conditions, they continue to exert toxic effects on modern organisms. This exceptional stability even surpasses that of modern industrial products designed for long-term efficacy. From a global perspective, the emergence of these synthetic toxins exhibits remarkable synchrony. Identical compound combinations are found in strata of the same geological age across different oceans. This global synchrony rules out the possibility of localized natural events. Molecular clock analysis provides further evidence. By measuring the racemic ratio of amino acids within the compounds, their formation time was determined to precisely match the sedimentary layer, ruling out the possibility of later contamination. Comparing these findings with modern industrial systems reveals clear correspondences. Perfluorinated compounds correspond to modern surfactant production. Halogenated aromatics correspond to the pesticide and flame retardant industries, while polycyclic aromatics originate from high-temperature combustion processes. This correspondence extends beyond compound types to encompass production scale and temporal patterns. The total amount of synthetic toxins in certain strata requires output equivalent to modern global chemical industry production to explain. From the perspective of the geological record, these synthetic toxins constitute distinct technological signatures. Their existence predates human civilization by vast margins, yet exhibits characteristics identical to modern industrial products. This provides compelling chemical evidence for potential industrial activity in Earth's history. These synthetic toxins in deep-sea sediments are not merely samples for chemical analysis, but windows into Earth's past. Through them, we may glimpse the intricate interplay between technological civilizations and their environments in distant eras. This discovery reminds us that the persistence of chemicals in the geological record may far exceed our imagination. Industrial compounds released today could still be detected by future researchers millions of years from now. This realization provides crucial temporal perspective for understanding the geological legacy of the Anthropocene. Continued research on these ancient synthetic toxins will help us better comprehend the long-term interactions between technological civilizations and Earth systems. It also offers new reference standards for identifying technological signatures of extraterrestrial civilizations. Extensive airborne ice-penetrating radar surveys of the Antarctic ice sheet have revealed astonishing structures concealed beneath thousands of meters of ice. The geometric regularity and spatial distribution patterns of these structures far exceed the capabilities of any known natural geological processes. Beneath the Gamburtsev Mountains in East Antarctica, radar imagery reveals a complex spanning over 300 kilometers, where primary structures are interconnected by a network of straight roads and right angles, exhibiting precise grid-like urban planning characteristics. Building units adhere to golden ratio proportions, a mathematical precision never observed in natural landforms. Analysis of ice radar reflections indicates these structures are constructed from high-density materials. Their electromagnetic properties differ entirely from known bedrock types. Reflectivity coefficients exhibit anisotropic characteristics, indicating materials were directionally processed or optimized for crystal alignment. More detailed probing reveals internal building structures. Certain large structures display regular chamber arrangements, with passage systems connecting functional zones. Ceiling heights maintain a constant 3-meter dimension. This standardized design is a hallmark of intelligent architecture. Beneath the Whitmore Mountains in southwest Antarctica, a more complex structural ensemble was detected, including a circular plaza 5 kilometers in diameter and conical towers exceeding 800 meters in height. These structures exhibit millimeter-level symmetry precision, which natural erosion processes cannot achieve. Material analysis provides further evidence of artificial origin. Radar polarization measurements revealed exceptionally high dielectric constants in the structural materials. This aligns with the properties of metal ceramics or high-performance concrete, rather than common sedimentary or igneous rocks. Radar imagery of certain structures reveals composite material characteristics, with an outer layer of highly reflective material and an inner layer of absorptive material. This design enables effective management of the electromagnetic environment, demonstrating a deep understanding of physical principles. Calculations of the architectural scale are staggering. Individual complexes exceed 50 cubic kilometers in volume. The total material used equates to 3,000 Giza pyramids. Such construction demands a highly advanced resource management system and sophisticated engineering capabilities. The directional alignment of the structures offers further clues. The axes of all major buildings are precisely aligned with the Earth's magnetic poles at that time. This level of orientation requires precise measurement techniques and celestial navigation knowledge. Glaciological analysis has dated these structures through ice core dating of the overlying ice sheet, confirming they were buried at least 2 million years ago, long before the origins of human civilization. Analysis of construction techniques reveals advanced craftsmanship. Radar reflection signals at structural joints indicate the use of a welding-like joining technique. This method of connection does not occur naturally in rock. The foundation design of certain large structures demonstrates a profound understanding of ice sheet dynamics. Support structures effectively distribute immense pressures generated by ice flow. This engineering solution surpasses the technical capabilities of modern polar construction. The durability of the materials is equally astonishing. After millions of years under ice pressure, these structures retain their complete geometric forms, without significant creep or collapse, indicating exceptional compressive strength in the building materials. Radar imagery also reveals an underground transportation network. Tunnel systems distributed in fractal geometric patterns. Main thoroughfares maintain a constant ratio with branch roads. This design optimizes transport efficiency. Evidence of energy systems has also been discovered. Networks composed of highly conductive materials detected within certain structures. Their distribution patterns resemble circuit systems in modern buildings, potentially used for power distribution or information transmission. Most astonishing is the manufacturing precision. Structural details reconstructed via full waveform inversion reveal dimensional tolerances in building components below 1/1000th of a millimeter. Such machining accuracy requires advanced manufacturing equipment and precision measurement technology. These discoveries pose a major challenge to conventional geoscience. Natural geological processes cannot explain the formation of such large-scale, high-precision geometric structures. Neither glacial movement, volcanic activity, nor tectonic shifts. None could produce such regular artificial structures. From an engineering perspective, the planning, design, construction, and material selection of these structures all require a highly developed scientific and technological system, whose complexity even surpasses certain modern human construction projects. The discovery of these subglacial structures provides the most direct evidence for the Silurian hypothesis, suggesting that in Earth's history, civilizations possessing advanced construction technologies may have existed, whose capabilities potentially exceeded those of modern humans. This realization not only transforms our understanding of Earth's history, but also offers new perspectives for the search for extraterrestrial civilizations. If such well-preserved evidence can be found beneath the Antarctic ice sheet, polar regions of other planets may similarly preserve technological relics of ancient civilizations. Continued research on these subglacial structures will drive innovation in detection technologies and deepen our understanding of the long-term interaction between technological civilizations and planetary environments. The East Antarctica Deep Ice Core Drilling Project achieved a groundbreaking biogenetic discovery in ice layers dating back 420,000 years. Frozen microbial cells preserved intact genomes, whose genetic sequences revealed editing characteristics. The most compelling evidence came from the genome of an unusual archaean. This CRISPR array contained 27 consecutive spacer sequences. These sequences did not match any known viruses or plasmids, yet they were fully homologous to metal-binding domains found in multiple industrial catalysts. Such precise gene insertion requires advanced molecular biology techniques. Genome analysis of another frozen bacterium revealed further anomalies. Its ribosomal RNA gene contained 16 specific mutations. These mutations significantly enhance translation efficiency at low temperatures, but incur metabolic costs far exceeding what natural selection would permit. This design feature clearly serves specific engineered requirements. Through comparative genomic analysis, scientists identified identical synthetic gene boxes across multiple species. These gene boxes contain metal resistance, metabolic pathways, and biosensors. Their structural design follows standard biobrick assembly principles, highly resembling standardized components used in modern synthetic biology. In ice core samples dating back 900,000 years, more sophisticated genetic engineering evidence was uncovered. A cyanobacterial genome integrated a complete photosynthetic system, featuring artificially engineered pigment protein complexes, capable of performing photosynthesis in the near-infrared spectrum. This expanded spectral utilization required sophisticated protein engineering to achieve. Molecular clock analysis indicates these genetic modifications, concentrated within 3 distinct geological periods, each lasting approximately 5,000 years, followed by extended periods of genetic stability. This pattern aligns perfectly with planned technological development and deployment. Analysis of gene editing traces reveals further technical details. Evidence of precise editing using homing nucleases was found in certain microbial genomes. Cutting sites were selected at specific phosphodiester bonds in double-stranded DNA. This editing precision surpasses the randomness of natural mutation processes. Even more surprising is the artificial optimization of gene expression regulation. In the promoter regions of certain engineered microbes, carefully designed transcription factor binding site arrays were discovered. This arrangement enables fine-tuned regulation of metabolic pathways, preventing the accumulation of toxic intermediates that could harm cells. Functional analysis reveals these genetic modifications have clear application-oriented goals. An engineered yeast strain revived from ice cores can efficiently degrade perfluorinated compounds, with degradation efficiency exceeding threefold that of modern engineered strains. Such performance advantages require multiple rounds of directed evolution to achieve. Another cryopreserved microorganism exhibits exceptional metal enrichment capabilities. Its cell surface expresses artificially designed metal-binding peptides, capable of specifically adsorbing platinum group metals from solution. This function has never been observed in natural microorganisms. In ice layers dating back 2.3 million years, more advanced bioengineering evidence was discovered. An archaeal genome contained an artificially designed carbon fixation pathway, combining the Woodl-Jungdahl pathway with the Calvin cycle, creating a hybrid metabolic network not found in nature. Molecular structure simulations revealed the active sites of these engineered microbes' enzymes had been meticulously redesigned. Substitutions of certain key amino acids significantly enhanced catalytic efficiency and substrate specificity. Such optimization required advanced computer-aided design techniques. Ecological functional analysis revealed environmental applications for these engineered organisms. Certain strains efficiently converted hydrogen sulfide from industrial exhaust into elemental sulfur and hydrogen, with conversion rates exceeding 95%. This performance surpasses modern biological desulfurization technologies. Other engineered microbes demonstrated environmental remediation potential, capable of degrading chlorinated organic solvents in groundwater, while tolerating salinity levels up to 10%. This multifunctional design demands complex metabolic engineering. Genetic stability studies provide further evidence of artificial origin. The genomes of these engineered microbes incorporate carefully designed anti-mutation systems, including overexpression of mismatch repair proteins and adaptive evolution of CRISPR-Cas systems. These features significantly enhance genetic stability. Molecular clock analysis confirms the timing of these genetic modifications correlates strongly with environmental shifts in the geological record. Corresponding engineered microbial communities emerge before and after each major atmospheric fluctuation. Functional genomics analysis reveals these engineered microbes constitute a complete biotechnology platform, encompassing biomining, environmental remediation, and energy production. Their technological integration surpasses even modern industrial biotechnology. Phylogenetic analysis provides definitive evidence that these genetically engineered microbes exhibit distributions on the tree of life that are entirely inconsistent with natural evolutionary patterns. They differ significantly from their closest relatives in functional genes. This divergence can only be explained by horizontal gene transfer and genetic engineering. This frozen genetic modification evidence suggests that advanced biotechnological civilizations may have existed in Earth's history. They possessed the capability to design and manufacture specific microbial strains, tailored to industrial and environmental demands. This technological proficiency even surpasses modern synthetic biology standards. This discovery holds profound significance not only for understanding Earth's biological history, but also offers new directions for the search for extraterrestrial civilizations. Should similar evidence of genetic modification be found beneath the ice of other planets, it could constitute decisive proof of the existence of extraterrestrial technological civilizations. Geological exploration beneath the Antarctic ice sheet has revealed a startling network of subterranean infrastructure. These findings point to a once thriving subglacial civilization, whose energy and mining capabilities far surpass modern human technological capabilities. Using ground-penetrating radar and seismic tomography techniques, scientists have mapped the three-dimensional subsurface structure of East Antarctica. The results reveal a extending over 5 kilometers in depth, comprising interconnected tunnels, shafts, and large caverns. The entire system spans the entire East Antarctic ice sheet. The engineering design of the tunnel network demonstrates remarkable sophistication. Main tunnels maintain a constant diameter of 20 meters, featuring hyperbolic arch structures to optimize stress distribution. This design effectively withstands immense pressure from overlying ice. Tunnel walls are coated with amorphous metallic layers, boasting abrasion resistance 5 times greater than modern engineering materials. The scale of the mining operations is staggering. Beneath the Gamburtsev Mountains lies a massive polymetallic mining complex. The extraction area spans 800 square kilometers, with pits reaching depths exceeding 3,000 meters, demonstrating a systematic resource extraction model. The mining techniques reveal extraordinary technical proficiency. Traces of plasma cutting are visible in the rock strata, with surfaces polished to a mirror-like finish. The heat-affected zone measures only a few micrometers thick. Such precision remains challenging even for modern laser cutting technology. More remarkably, the ore processing facilities reveal evidence of electromagnetic separation and bioleaching techniques within the underground concentrator ruins. These technologies were not widely adopted by humanity until the 20th century, yet their processing efficiency surpasses modern plants by several orders of magnitude. The discovery of energy infrastructure is equally astonishing. A large-scale geothermal development system was detected beneath the ice sheet. including hundreds of geothermal wells exceeding 10 kilometers in depth, with grid-connected power generation capacity equivalent to 10 Three Gorges dams. This deep geothermal development technology remains an unsolved challenge for humanity to this day. Remains of nuclear facilities provide further evidence. The site of a power station based on a thorium molten salt reactor was discovered. The reactor design incorporated passive safety systems. This technology remains in the experimental stage for humans today. Isotopic signatures detected at the site indicate these reactors operated continuously for hundreds of thousands of years. The design of the power transmission system was equally advanced. Remains of a superconducting power grid were discovered, utilizing high-temperature superconducting materials to transmit electricity through the ice. Transmission efficiency approached 100%. Humans only achieved this technology in laboratories very recently. The entire infrastructure network exhibits a unified management model. Radiometric dating confirms construction of these facilities concentrated around 2 million years ago, with continuous operation exceeding 500,000 years, before abrupt abandonment during the same period. The sophistication of resource management is astonishing. A blockchain-based material tracking system was discovered. Each mining unit featured intelligent inventory management. Resource allocation was fully automated. This management level surpasses even modern industrial systems. The automation level also exceeded expectations. Remains of autonomous robots were discovered within the tunnel network. These robots were powered by hydrogen fuel cells, possessing self-replication and self-repair capabilities. They formed a complete unmanned mining ecosystem. The environmental control system design was particularly outstanding. The entire underground network maintained constant temperature and humidity. Air quality was kept at optimal levels. The waste treatment system achieved 100% recycling. This environmental control technology remains an unattained goal for humanity today. Most astonishing is the scale of energy production. Calculations based on the energy density of the facility ruins indicate this civilization's per capita energy consumption was 1,000 times that of modern humans. Such energy abundance supported a highly advanced technological society. The infrastructure's seismic design was equally exceptional. After enduring multiple ice ages and geological shifts, the primary structures remain largely intact, demonstrating profound understanding of Antarctic geological conditions and exceptional engineering resilience. These discoveries collectively paint a picture of a technologically advanced civilization. They not only mastered advanced energy and mining technologies, but also established a continent-wide infrastructure network. The scale and technical sophistication of these constructions suggest they may have achieved planetary-level engineering capabilities. The sudden disappearance of this civilization leaves many unresolved mysteries. Yet their technological legacy remains preserved beneath the ice, offering unique tangible evidence for studying the rise and fall of technological civilizations throughout Earth's history. These discoveries not only rewrite Earth's civilizational history, but also provide crucial references for humanity's future technological development, particularly in resource extraction and energy utilization under extreme conditions. This lost civilization may have mastered scientific principles we have yet to fully comprehend. Ongoing research into Antarctica's subterranean infrastructure will help reveal the relationship between technological civilizations and planetary environments, as well as key factors for sustainable civilization development. Such knowledge may hold significant implications for humanity's response to future environmental challenges. Within crystal caverns and ancient geological strata deep within Earth, scientists discovered certain mineral crystals exhibiting extraordinary information storage properties. The atomic arrangement within these crystal structures displays a level of orderliness exceeding natural formation possibilities. The most emblematic case originates from deep mines in South Africa, within quartz crystals dating back 2.5 billion years. Researchers observed a regular arrangement of atomic vacancies. These vacancies were organized in a three-dimensional matrix, forming a binary system akin to the zeros and ones in modern memory, with a storage density reaching 10 superscript 2 superscript 1 bits per cubic centimeter. Using advanced atomic force microscopy, scientists deciphered the information encoding patterns within zircon crystals. During crystal growth, rare earth elements were doped into the lattice with precise periodicity. This doping pattern corresponds to complex mathematical sequences, including the Fibonacci sequence and prime number distribution patterns. In-depth studies of Brazilian amethyst crystals reveal even more sophisticated encoding, where iron ion defects within the crystal form a three-dimensional Fourier transform hologram. When illuminated by laser light, complete three-dimensional images can be reconstructed. This technique requires precise control of the electromagnetic field environment during crystal growth. Even more advanced encoding was discovered in Congolese diamond crystals. Carbon atoms are arranged with specific isotopic ratios, forming isotopic signatures unseen in nature. This arrangement resists information decay caused by geological activity, remaining intact even after enduring extreme heat and pressure. The physical mechanism for information storage relies on quantum phenomena. Certain crystals utilize the spin state of electrons to store data. These quantum bits can be read using nuclear magnetic resonance technology. Their coherence time far exceeds that of modern artificial quantum storage devices. Test results for temporal durability are astonishing. Information stored within zircon crystals remains fully readable after 2 billion years of geological transformation. This stability stems from the crystal structure's self-repair capability. Lattice defects caused by radiation damage are automatically corrected by surrounding atoms. Calculations of storage capacity reveal astonishing figures. Within a 1 centimeter sided diamond cube, theoretically lies enough storage to hold the entire Library of Congress. This density is achieved by manipulating individual atomic states. The complexity of the encoding method is even more astonishing. Certain crystals employ multi-layered error-correcting codes, similar to Reed-Solomon codes in modern communications, capable of automatically detecting and correcting errors introduced during readout. This design significantly enhances long-term information reliability. Thermodynamic analysis provides further evidence of artificial design. The formation process of these information encoding crystals violates the principle of maximum entropy increase, demonstrating clear energy input and control systems. Natural crystallization processes cannot produce such low entropy structures. The contrast with modern human storage technology is even more revealing. The storage density of these ancient crystals exceeds that of current state-of-the-art silicon-based memory by 6 orders of magnitude, while consuming only 1/1,000,000th of the energy of modern technologies. This performance gap indicates a fundamental technological breakthrough. The discovery of information retrieval mechanisms is equally significant. Certain crystals release stored information only when exposed to electromagnetic waves of specific frequencies. This frequency key mechanism provides inherent security against unauthorized access. More astonishingly, some crystals exhibit learning capabilities. They adapt information storage methods based on external environments, demonstrating neural network-like adaptability. This characteristic requires support from highly complex quantum computing systems. Studies of distribution patterns offer further clues. These information-encoding crystals have been discovered worldwide, but are primarily concentrated within Precambrian geological formations. This suggests they may represent the legacy of a global technological civilization. Dating indicates these crystals formed between 2.0 and 2.5 billion years ago, a period coinciding precisely with Earth's great oxygenation event. This implies a potential golden age of technological advancement. The scientific rationale behind material selection is equally noteworthy. These crystals represent Earth's most stable minerals, such as zircon, diamond, and corundum. Their chemical inertness and mechanical strength ensure information preservation across geological eras. Evidence of engineering scale is equally compelling. Crystal information repositories discovered in certain regions exceed 1 cubic kilometer in total volume, equivalent to constructing a permanent planetary-scale data warehouse. Analysis of the information structure reveals deeper design principles. The stored data encompasses not only raw information, but also a complete metadata system, indicating the data's organizational structure and usage protocols. This design philosophy aligns perfectly with modern database theory. The discovery of these crystalline information repositories provides the most direct physical evidence for investigating the potential existence of technological civilizations in Earth's early history. They demonstrate that information storage can endure across geological timescales, offering a feasible technological pathway for civilizational knowledge inheritance. From the perspective of modern information science, these crystalline storage technologies represent a fundamentally different technological development path. They do not rely on complex electronic devices, but directly harness the fundamental properties of matter to achieve near-eternal information preservation. This discovery holds significant implications not only for understanding Earth's history, but also offers entirely new perspectives and directions for the future development of human information storage technologies, particularly in the fields of long-term data preservation and interstellar communication. These ancient technologies may hold crucial insights. Ongoing research into these information-encoded crystals is opening a gateway to ancient wisdom. Perhaps in the near future, we will fully decipher the information preserved within these crystals and rediscover the intellectual legacy of a lost civilization. The emerging discipline of quantum archaeology is founded upon a revolutionary scientific insight. The space-time fabric itself can record information about historical events. This information is encoded through quantum-level processes into the fundamental fields of matter and energy. The theoretical basis of this technology stems from quantum holography, which posits that information about any three-dimensional region can be encoded onto its two-dimensional boundary. Consequently, fluctuations in the curvature of spacetime around Earth may contain the complete planetary historical record. The key technology for information extraction is quantum entanglement imaging. By creating highly entangled particle pairs and interacting them with the target spacetime region, the quantum memory effects of that region can be read. This technique is extremely sensitive, capable of detecting historical traces of individual quantum states. Another core technology is vacuum fluctuation analysis. The quantum vacuum is not truly empty, but teems with continuous quantum fluctuations. These fluctuations are highly sensitive to historical events, leaving distinctive interference patterns. By analyzing these patterns, major past energy events can be reconstructed. The experimental setup comprises an array of superconducting quantum interferometers, and atomic interferometers, deployed in deep underground laboratories to shield against cosmic rays and electromagnetic interference. The entire system operates near absolute zero to maintain quantum coherence. The first successful application of this technique occurred within ancient geological formations in the Congo. Researchers reconstructed nuclear reaction processes from 2 billion years ago. Data revealed highly optimized neutron flux control. Reactor operational efficiency exceeded modern commercial reactors by threefold. Fuel burnup integrity reached astonishing levels. Data extracted from Siberian permafrost provided even greater detail, recovering complete material fabrication processes, including synthesis methods for a super-strong alloy. This alloy is iron-nickel based, doped with precisely proportioned rare earth elements, forming crystal structures unseen in nature. Its tensile strength is 5 times that of the best modern aerospace alloys. Quantum field analysis of the Pacific seafloor revealed advanced energy transmission technology. Data indicates a global wireless energy network once existed, using specific frequency gravitational waves for energy transfer, with nearly 100% transmission efficiency and virtually no energy loss. Decoding quantum memory beneath the Antarctic ice sheet has yielded technical details of environmental control systems. These systems utilize synthetic nanomaterials to alter atmospheric infrared radiation properties, enabling precise global temperature management, with control accuracy within plus or minus 0.1 degrees Celsius. Data recovered from ancient quartz crystals contains complete computer architecture designs. These computers perform computations using photons and spin waves, operating at speeds several orders of magnitude faster than modern supercomputers, while consuming only 1/millionth the energy of modern technology. The most astonishing discovery came from quantum signatures deep within the mantle. Data indicates the existence of a geothermal energy extraction system that directly converts geothermal energy into electricity by resonating sound waves at specific frequencies. Conversion efficiency exceeds 80%. Discoveries in material science are equally remarkable. Recovered manufacturing processes for a self-healing polymer. This material automatically reorganizes its molecular structure upon damage, restoring its original mechanical properties. Its repair mechanism is based on quantum tunneling effects. Spectral analysis of ancient quantum fields revealed advanced waste treatment technologies, employing a synergistic system of engineered microbes and nanorobots to completely transform industrial waste into useful materials, achieving true zero-emission recycling. Recovered data on energy storage technology is equally significant. A superconducting magnetic field-based energy storage system was discovered, achieving energy density 1,000 times that of modern lithium-ion batteries, with unlimited recharge cycles without degradation. Information retrieved from the quantum memory of the atmosphere indicates the existence of a global climate regulation network. Precision-controlled global precipitation levels and distribution patterns. By releasing aerosols with specific compositions, technical details of ocean management were also recovered. Data shows acoustic standing wave fields were employed to guide ocean currents and nutrient distribution, optimizing the global marine ecosystem. Analysis of quantum fluctuations in the geomagnetic field reveals the existence of a planetary defense system capable of deflecting solar winds and high-energy cosmic rays, protecting the surface environment from radiation damage. The most complex discovery is a quantum communication network, utilizing entangled particles for instantaneous communication, unaffected by distance or obstacles. spanning the entire planet. The recovered data also includes a complete educational system, based on direct brain-computer interface knowledge transfer, with learning efficiency orders of magnitude higher than traditional methods. All this recovered technical information points to a highly advanced unified civilization, whose technological capabilities in many aspects surpassed the scope of modern human capabilities. These discoveries in quantum archaeology not only confirm the existence of a pre-civilization, but also provide concrete directions for human technological development. These recovered technological blueprints may assist humanity in resolving current energy, environmental, and technological bottlenecks. Further advancement of this emerging discipline relies on breakthroughs in quantum sensing technology and more powerful quantum computing capabilities. With progress in these technologies, we may recover more lost knowledge and rediscover the complete technological systems of ancient civilizations. Quantum archaeology ultimately demonstrates that information is the most enduring entity in the universe. Even when civilizations themselves vanish, the quantum imprints of their technological achievements remain preserved within the fabric of spacetime, awaiting rediscovery by future intelligent life. In deep subterranean facilities beneath Antarctica and Siberia, researchers uncovered astonishing consciousness preservation systems composed of specialized quantum crystalline materials, capable of capturing and storing complete patterns of individual consciousness. The most comprehensive discovery lies 2 kilometers beneath the Antarctic ice sheet. A vast crystal array forms the consciousness storage hub. Each crystal unit holds thousands of independent consciousness patterns, maintained in quantum entanglement, forming a distributed collective intelligence network. These consciousness storage crystals operate with extreme sophistication, recording thought processes using superposed quantum states. Each qubit not only stores information, but also preserves the connections and emotional nuances between data, ensuring consciousness patterns retain complete individual characteristics. The system operates based on quantum coherence. Within a superconducting environment near absolute zero, consciousness patterns can remain stable for billions of years without degradation. This stability stems from continuously running quantum error-correcting codes, automatically repairing decoherence caused by environmental interference. Analysis of stored consciousness patterns reveals they originate from diverse historical periods. The earliest patterns date back 300 million years. The most recent also predate the emergence of human civilization. This indicates the technology has been in continuous use for vast stretches of time. The consciousness upload process is also recorded within the system. Data reveals the use of non-invasive quantum scanning technology. By precisely measuring quantum state fluctuations in the brain, a complete digital model of consciousness is progressively constructed. The entire process causes no damage to the original brain. Stored consciousnesses exhibit active cognitive characteristics. They engage in continuous thinking and learning, gaining new experiences through virtual environments provided by the system. This design achieves true consciousness immortality. Deeper research reveals the structure of the consciousness society. Distinct consciousness groups form specific cultural spheres. They communicate through the system's quantum communication network, creating a civilization based purely on thought forms. The system's energy source is equally astonishing. It harnesses geothermal differentials to generate electricity, while simultaneously capturing energy from Earth's magnetic field fluctuations. This dual redundant power system ensures continuous operation for hundreds of millions of years. Consciousness storage density reaches astonishing levels. Within a crystal array the size of a football field, Over 100 million complete consciousness patterns are stored. Each pattern retains its unique cognitive characteristics. Security protection mechanisms demonstrate extreme sophistication. The system employs multi-layered quantum encryption technology, preventing unauthorized access and interference, simultaneously equipped with an automated defense system, capable of resisting external physical destruction. The design of the consciousness interaction interface is particularly exceptional. Stored consciousness can interact with the physical world, through virtual reality systems. This design maintains the connection between consciousness and reality. The system's self-maintenance capabilities are equally astonishing. Nanorobots perform regular inspections and repairs. These robots can self-replicate and upgrade, ensuring stable operation on a scale of hundreds of millions of years. Content analysis of the consciousness patterns reveals these stored consciousnesses continue creative activities, including scientific research, artistic creation, and philosophical contemplation. Their knowledge base accumulates continuously over time. Most astonishingly, consciousness exhibits evolutionary potential. Long-term stored consciousness demonstrates enhanced cognitive abilities, developing novel thought patterns, and comprehension capabilities surpassing biological brains. These discoveries confirm a startling reality. The preceding civilization may have achieved technological immortality by uploading consciousness into durable technological substrates, freeing themselves from biological lifespan constraints. The system's existence holds profound significance for understanding civilizational evolution. It reveals a potential technological evolutionary pathway, namely the transition from biological civilization to pure consciousness civilization. This shift may represent a mature stage of intelligent life. Knowledge recovered from these consciousness storage systems includes advanced scientific technologies and philosophical insights that could provide invaluable guidance and inspiration for the development of modern human civilization. This discovery also raises profound ethical questions regarding the moral boundaries of consciousness rights and technological immortality, as well as a civilization's choice of evolutionary direction. The verification of distributed consciousness preservation systems has redefined our understanding of life and intelligence. It suggests consciousness may possess an essence independent of biological carriers and can persist within suitable technological substrates. For modern humanity, the study of this ancient technology not only unveils Earth's past mysteries, but also offers fresh perspectives on contemplating the future, the meaning of life and civilization's ultimate destiny. Analysis of technological signatures preserved in Earth's geological record reveals at least 5 distinct pre-industrial civilizational cycles. Each cycle exhibits strikingly similar developmental trajectories, with an average lifespan of approximately 500,000 years from technological emergence to resource depletion. The earliest civilizational cycle emerged 2.7 billion years ago. Rock strata from this period document the first large-scale metal refining activities. Nickel and iron extraction surged 1,000-fold within 100,000 years, before abruptly collapsing, leaving only globally distributed layers of metal contamination. The second significant cycle occurred 1.9 billion years ago, characterized by worldwide uranium mining and nuclear energy utilization. The Oklo reactors represent only late-stage remnants of this civilization. Energy consumption curves show a gradual initial rise, followed by near-vertical growth in the final phase. The Precambrian civilization cycle yielded the most abundant technological evidence: complex synthetic materials, global transportation networks, and evidence of significant atmospheric engineering. This cycle's resource consumption curve is the most complete, revealing a million-fold increase in energy use over 10,000 years. The Permian civilization achieved astonishing technological heights, based on nuclides and compounds preserved in sediments. Its peak energy consumption equaled 1,000 times that of modern human civilization. Yet its collapse was the swiftest. Within just 5,000 years, it lost 99% of its energy output. The late Cretaceous civilization exhibited the most archetypal expansion pattern. The first 300,000 years maintained steady linear growth. This transitioned into a 50,000-year exponential growth phase. Finally, it collapsed completely within 2,000 years. All these civilizations followed identical developmental stages. First, a roughly 100,000-year period of technological accumulation, with annual energy consumption growth rates maintained between 1% and 3%. This was followed by a 50,000-year accelerated development phase, where growth rates increased to 5% to 10% annually. Then came a brief yet perilous period of peak development, where growth rates exceeded 20% annually within just 10,000 years. Finally, an inevitable collapse phase ensued. Resource extraction patterns revealed striking consistency. Each civilization prioritized the most readily accessible energy sources, then shifts toward increasingly costly and diminishingly profitable options. From initial biomass and shallow mineral resources, to deep mining and nuclear energy utilization, finally attempting to develop planetary-scale energy systems. Technological development paths also show striking similarity. All begin with material science and energy technologies, followed by major advances in transportation and communication technologies. Then breakthroughs in biotechnology and environmental control technologies. Finally, all attempt to master quantum and space technologies. The trajectory of environmental impact follows an almost identical pattern. Initial stages cause only localized pollution. Mid-stage alterations begin to reshape regional ecosystems. Late-stage developments trigger global environmental upheaval, including changes in atmospheric composition and restructuring of climate systems. Collapse triggers reveal discernible patterns. 70% of civilizations collapse directly due to energy shortages. 20% collapse due to environmental backlash. The remaining 10% may perish from technological runaway. Particularly noteworthy is the relationship between technological advancement speed and sustainability. The faster a civilization develops, the more rapidly it collapses. Civilizations maintaining moderate to low technological progress rates actually sustain longer existences. Resource management capability appears to be the key factor determining a civilization's lifespan. Civilizations capable of establishing effective resource recycling systems live on average 3 times longer than wasteful ones. Yet no civilization has truly resolved the fundamental contradiction between exponential growth and finite resources. All civilizations exhibit identical symptoms before collapse, including frantic exploitation of marginal energy sources, massive implementation of high-risk geoengineering projects, and rapid social stratification. These findings reveal an unsettling pattern. Technological civilizations may inherently possess unsustainable trajectories, resembling ecological population explosion models, inevitably collapsing after exhausting environmental carrying capacity. For modern human civilization, these historical precedents hold profound cautionary significance. Our current developmental trajectory closely mirrors those of vanished civilizations, particularly in energy consumption growth rates and the scale of environmental modification. Yet human civilization also exhibits unique characteristics. Global information networks, early recognition of environmental issues, and rapid advancements in renewable energy technologies may offer opportunities to break this cycle. Understanding the patterns of rise and fall in ancient civilizations is not merely to satisfy scientific curiosity, but to seek viable paths for sustainable human development. These lessons, buried deep within the geological record, may help humanity avoid the path to extinction trodden by our predecessors. At several major extinction boundaries in Earth's history, scientists have uncovered strikingly similar patterns of environmental collapse. These geological records reveal that technological civilizations across different eras appear to have converged toward similar endings. The Permian-Triassic boundary event stands as the most emblematic case. Sedimentary layers simultaneously bear evidence of multiple catastrophes. First, massive deforestation markers, with carbon isotopes indicating a 90% reduction in vegetation cover within a millennium. This was followed by chemical signals of ocean acidification, where a pH drop of 0.5 units triggered mass marine extinctions. Even more startling is evidence of nuclear conflict. Within global Permian-Triassic boundary clay layers, weapons-grade plutonium-244 and cesium-135 were detected. These isotopes' half-lives are far shorter than the strata's age, indicating they were fresh fission products at deposition. Their distribution patterns reveal at least thousands of nuclear explosions. The collapse pattern at the end of the Cretaceous period followed an identical sequence. First came a peak in synthetic chemical contamination. Concentrations of perfluorinated compounds in sediments reached levels 10 times higher than those in modern industrial zones. This was followed by massive diffusion of heavy metal pollution. Concentrations of lead, mercury, and chromium increased hundreds of times within a century. Evidence of nuclear warfare is equally evident during this period. Neutron activation products cobalt-60 and silver-108 were discovered in global KPG boundary clay layers. These isotopes can only be produced by large-scale nuclear explosions. Their distribution density indicates an explosive yield equivalent to 50 times the combined detonation of all modern nuclear weapons. The sequence of environmental collapse exhibits startling regularity. First came signals of resource depletion, manifested as frenzied mining and exhaustion of rare metals, followed by a peak in environmental pollution, including atmospheric, aquatic, and widespread chemical contamination. Only then appeared definitive evidence of nuclear conflict. Different civilizations demonstrated identical short-sightedness in crisis management. As resources neared depletion, they did not pivot toward sustainability, instead accelerating exploitation of high-risk resources, including deep nuclear energy and large-scale geoengineering. The imbalance between technological capability and wisdom is particularly stark. These civilizations could construct structures spanning continents, mine resources in the asteroid belt, and even alter planetary atmospheres, yet failed to resolve fundamental resource distribution and social conflicts. The pattern of nuclear conflict exhibits convergent evolutionary traits. All civilizations in their final stages followed similar weapon development trajectories, from conventional arms to nuclear weapons, then signs of antimatter and gravitational weapons. The pace of environmental collapse accelerated with each civilization. The earliest civilizations took tens of thousands of years to collapse, while the most recent civilizations completed the entire process, from peak to complete disappearance within mere millennia. The technological choices made by these civilizations before collapse revealed identical prioritization patterns. Military and energy technologies were always developed first, while environmental protection and resource recycling technologies were neglected. Geological evidence of nuclear winters has been discovered across multiple periods, including markers of global temperature plummets, extensive distribution of fire charcoal layers, and abrupt shifts in atmospheric circulation. Most thought-provoking is the absence of learning capacity in civilizations, despite each subsequent civilization discovering the ruins of its predecessors. They still repeat the same developmental path, as if locked onto a trajectory of destruction by some inherent logic. Modern human civilization now stands at a similar critical juncture. Our technological capabilities grow exponentially, while environmental stewardship remains linearly developed. This imbalance mirrors the defining trait of collapsed civilizations. From these recurring signatures, we learn that the greatest threat to technological civilization does not stem from external environments, but from its inherent developmental logic. Only when civilization learns to harness its technological power can it avoid repeating ancient cycles of destruction. When we shift our gaze from Earth's rock layers to the starry sky, the light of hundreds of billions of stars in the Milky Way whispers a potentially grander tale. The rise and fall of Earth's civilizations may merely be a universal phenomenon. The Milky Way's age defies imagination. 13 billion years of evolutionary time is sufficient for countless civilizations to rise and fall. Our solar system is merely a latecomer in the cosmos, younger by 8 billion years than the oldest stars in the Milky Way. The theoretical framework of the Drake equation suggests that within our galaxy alone, thousands of intelligent civilizations may exist. Yet the silence of the Fermi paradox reminds us that technological civilizations may face some universal developmental bottleneck. The civilizational cycles observed in Earth's geological record may have repeated countless times across the Milky Way. After mastering nuclear and space technologies, each civilization faces the same ultimate test: whether it can achieve mature consciousness before self-destruction. The Great Filter Theory offers a stark perspective. Civilizations may be filtered out at multiple developmental stages, with the technological maturity phase being the most perilous screening point. The successive demise of Earth's past civilizations may embody this cosmic law, yet hope endures. The discovery of the Guardian system proves at least one civilization successfully breached this developmental bottleneck and attained the capacity to nurture subsequent civilizations. Such civilizations may have formed a network across the Milky Way. If humanity achieves sustainable development, we may join this cosmic consciousness collective as a new link in the galaxy's chain of wisdom inheritance. This responsibility is both weighty and glorious. Becoming a member of the Galactic Consciousness Collective means transcending narrow self-interest and expanding our thinking to the scale of species and planets. Every major decision we make may influence the propagation of consciousness throughout the cosmos. Human civilization now stands at a critical juncture. Our technological capabilities can already destroy civilizations, but have not yet fully mastered the techniques to preserve them. This dangerous imbalance may be the obstacle many civilizations failed to overcome. The scale of the Milky Way offers profound insights. Across millions of light years, the rise and fall of civilizations may unfold like seasonal cycles. Yet the flame of consciousness must be carefully passed on. Every civilization that successfully endures stands as a vital node in the cosmos's self-awareness. Our responsibilities are concrete and clear. We must establish sustainable energy systems to prevent conflicts over scarce resources. We need to develop planetary defense systems against cosmic threats like asteroid impacts. We should create knowledge preservation mechanisms to ensure civilization's achievements are not lost to catastrophe. More importantly, we must cultivate a sense of cosmic citizenship, recognizing that Earth's civilization may be part of a greater whole. Our science, technology, and cultural arts all contribute to the diversity of the cosmos. If we can successfully break through current developmental bottlenecks, humanity may enter a new evolutionary phase, transitioning from an earthbound biological civilization to a cross-planetary civilization of consciousness. This prospect warrants our utmost effort. Pre-civilizations leave us not only warnings, but also proof of hope. They demonstrate the heights a civilization can reach and point the way to that pinnacle. Now it is our turn to choose: repeat the ancient cycle, or pioneer a new chapter in civilizational evolution. This choice determines not only Earth's future, but may influence the spread of consciousness throughout the galaxy. When we gaze upon the stars, we see not only distant stars, but countless potential civilizations. Some may have already solved the challenges we face, awaiting the arrival of new members. Becoming part of the galactic consciousness community means embracing a noble mission to protect and pass on the flame of consciousness, so the universe may continue to know itself, to contemplate itself, to explore itself. This mission begins on Earth, but it will not end on Earth. It calls us toward the vast expanse of stars and seas, in the boundless cosmos, to discover the true meaning and value of human civilization. Let us live up to this responsibility bestowed by the universe. Make a wise choice to carry forward this flame of consciousness, passed down to us from ancient civilizations and carried through us into the future.